So today we'll be going over some concepts from Chapter 3, our chi-square and pedigree. Introduction of our chi-square test. The book tells us that it's the probability that the difference between the observed and the expected value is due to chance. I like to think of this in a little bit of a different way. I like to say that the chi-square is a measurement of how well observed values match our calculated theoretical values. A big part of using a chi-square table, which we'll get into later, is degrees of freedom. Degrees of freedom is the amount the sample size can vary. This picture here is from the text, and I don't really like how the text gives the definition because it can be a little more confusing. So I'm going to show a more practical example. So let's just ignore that for now, and I'll explain my way of degrees of freedom. So say that you're making some meal plans and you want to have a different meal for dinner each of the 7 days a week, and you have choices between tacos, spaghetti, sushi, stir fry, pizza, beef stew, and pancakes. Our days of the week here, and I have this organized through the days of the week up top and our number of choices in this row. So on Monday, you have seven different choices, and you choose tacos. So tacos is off our list. You get to Tuesday, and you're left with 6 choices between spaghetti, sushi, stir fry, pizza, beef stew, and pancakes. And you choose sushi. So now sushi's off your list. Tuesday, you only have 5 choices, and you choose pizza. Thursday, you choose pancakes. Friday, you choose spaghetti. Saturday, you choose stir fry. And by the time you get to Sunday, you only have 1 choice left, and that's beef stew. So when you get to Sunday, you've used up all of your freedom to choose, and you're left with only 1 choice. This is how I like to look at degrees of freedom. So basically, your degrees of freedom is always going to be the number of choices you have, or in genetics, the number of phenotypes that are presenting, minus 1. So in this example, we have 7 choices, minus 1 equals 6. So 6 is our degrees of freedom in this example. Now, to use your degrees of freedom and your critical values of the chi-square, start with your degrees of freedom. So you look down your degrees of freedom column, and let's just say we had the 6. So here's our 6 here. After we calculate our chi-square values, which we'll do in an example here in a minute, we go across this column and find one that's close to ours. So you go across the column left to right, or the row left to right. So let's go into a quick, more conceptual example of this, and then we'll go into a detailed example. The flowchart we'll be using, and it is a good general layout of how the problems like this will go. I'm going to break this flow chart into 3 parts. This yellow part here will be our monohybrid crosses and the self-fertilization of the first generation. The purple part, I'll go into detail about how to calculate the chi-square for each phenotype. And then we'll go to our degrees of freedom and analyzing the chi-square results. So here we have 2 parents, a purple and a white, and big P, little p. I have up here in this corner the genotypic cross rather than the phenotypic cross. So we cross these 2, and we can easily see that all of the first progeny will be heterozygotes, but they will be phenotypically purple. And then through self-fertilization, we should end up with 3/4 of the population being purple and 1/4 of the population being white. But however, what we observed is 105 of these individuals are purple and 45 of them are white. So let's figure out how well what we've observed fits with our theorized values. So whenever you're doing these chi-square analysis, these three numbers are going to be the most important when you first start out. So you want to total up how many of the individuals you had. And then you want to figure out theoretically what that is supposed to be. What is the expected value? What theoretically you would have gotten from a perfect cross. So 3/4 of 150 is 112.5, and then 1/4 of that is 7.5. So now that we know our expected values and our observed values, we can go on to evaluating the chi-square. So this is our equation right here. What we're going to do is do a chi-square analysis for the purple and for the white, and then we're going to add them together, which is what this sigma sign means. And your O here stands for observed minus expected. You square that value and then you divide it by the expected. After we do all that math, we find that our chi-square value is 2.0. Now we have to determine our degrees of freedom. So degrees of freedom equals n minus 1. And for this, we only had 2 phenotypes. So 2 minus 1 is 1. Our degrees of freedom is only 1. I have those. Let's go to the table to look at the critical value. So we determined that our degrees of freedom was 1. We always want to start with that. And then we're going to go along this line right here and find where 2.7 might lie. And it looks like it's in this gap right here. And that's going to put us between these two values. So when the critical value is less than 0.05, we can say that we've observed a significant difference between the theoretical and observed values. But ours is between 0.5 and 0.1. So we didn't really observe anything significantly different than what we expected. So let's apply that overview to an actual problem. We're told that purple kernels are dominant over yellow kernels and full kernels are dominant over shrunken kernels. We crossed a corn plant with purple and full kernels, and then another one with yellow and shrunken kernels, and then we obtained these progenies, the likely genotypes of the parents and the progeny. And then we have to test our hypothesis with the chi-square test. So to solve this problem, we need our phenotypic ratios of the progeny, and we need the genotypes and phenotypes of the progeny and the parents. We'll also need our degrees of freedom, and then we'll need our chi-square equation. So let's get to it. What information are we given? We're only given the progeny of the phenotypes. So we're going to have to treat this in a multi-step process. So when we analyze the color and shape traits separately, we can kind of get a better grasp on what's expected versus what we observed. So this table here just shows that the two traits that we are observing, and we've added them up. I just took this purple here, it's 112, and then this other purple is 103. So in total, we have 215 purples, 185 yellow, 203 full, and 197 shrunken. So now we can put those back together, and it's just all of these added up. There's a total of 400 progenies. So how can we determine the genotypes of the parents? when we do a monohybrid cross between a homozygous dominant and a homozygous recessive, all the progeny are going to be dominant. So that gives us a 1-to-0 ratio. When we do two heterozygotes, it's a 3-to-1 ratio. But when we cross a heterozygote and a homozygous recessive, it's a 1-to-1 ratio. So in that table we saw earlier, our ratio of purple to yellow is 215 to 185, and full to shrunken is 203 to 197. So our parents are likely and then a homozygote recessive. So in order to do our chi-square analysis, we need to find what was expected. So I made this table, and we must determine the progeny of the dihybrid cross. So these are the possible combinations of the heterozygous parent. For the homozygous recessive parent, you only have one option. So these 4 phenotypes ensue from that dihybrid cross. So we'll have a purple full, a purple shrunken, a yellow full, and a yellow shrunken. And these are our observed values that we were given up here. We have 4 phenotypes, and we should expect a 1-to-1 ratio. That means that we should expect a quarter of each of these, so 100 for each of these traits. So next we need to calculate our chi-square values for each phenotype using our chi-square equation. And this is really just a plug-and-play type of thing. We know our expected for every single one, so we're always going to divide by 100. Our observed comes from this table right up here. So we just take 112 minus 100, and then we square that and divide it by 100. And that gives us the chi-square value for our full purple progeny, and for our shrunken purple, for our full yellow, and for our shrunken yellow. Now what trips a lot of people up is that this sigma here, you have to add all of these values to get your total chi-square value. That's what the sigma means. It means sum. So now that we have this, our next step is to analyze it. But first, before we go to the table, we need degrees of freedom. Since we had 4 different choices to choose from, we subtract 1, that equals 3. So degrees of freedom for this cross is 3. So let's go to our table here. Knowing that our degrees of freedom is 3, we can go to our 3, and then we'll go across this row until we hit a gap that's about 2.7. Looks like it's going to be that gap right there. And that associates with a p-value that's between 0.1 and 0.5. This just means that our observed results were not significantly different from the expected results. You could also say that we got what we expected. So let's go switch gears now to our pedigrees. The column's kind of long, so I'll just breeze through this really quickly. It's worded very, very long. So Joanna has short fingers. Her 2 older brothers are identical twins. They also have short fingers. Joanna's 2 younger sisters have normal fingers. Her mother's normal. Her father has short fingers. Her paternal grandmother has short fingers. Her paternal grandfather had normal fingers, and he's now dead. Both of Joanna's maternal grandparents have normal fingers. Joanna eventually marries Tom, who has normal fingers. They adopt a son named Bill, who has normal fingers, whose biological parents have normal fingers. After adopting Bill, Joanna and Tom produced 2 children, an older daughter with short fingers and a younger son with normal fingers. So this is the pedigree that I will be referring to throughout this problem. So we're asked, what's the most likely mode of inheritance for short fingers in this family? Now I've highlighted a few things. because there's an affected individual in each generation, we can immediately rule out any kind of recessive inheritance, meaning autosomal or X-linked recessive. These recessive traits, they tend to skip generations, so that's out. The X-linked dominant trait, we can also rule out because Joanna here, her father, a presenter of this trait, and if it was an X-linked dominant trait, he can only supply an X dominant for this. So every individual in this, his offspring, would express that trait. And we can also rule out Y-linked because obviously we have women that are presenting. So since we've ruled all those out, we can conclude that condition is most likely autosomal dominant. So since we figured that out, now we have to find the probability that if Tom and Joanna have another biological child, how likely is it that the child will have short fingers? To do this, we need to figure out the genotype of Joanna. Since this is an autosomal dominant trait, we already know that Tom is homozygous recessive because he is not presenting the trait. So here's Joanna. We know that she must have at least one dominant copy of the allele to express the trait. Here's her mother. Since she is not presenting, she must be homozygous recessive. And here's her father. So how can we figure out her father's to determine her genotype? Since some of her siblings do not express the trait, her father has to be heterozygous, because if he was homozygous, that's the only trait that he could provide. So all of the offspring from her father would be affected by the condition if he was a homozygous dominant, because her father can't be the homozygous dominant because all of his children would have that. And a cross between a heterozygous dominant and homozygous, heterozygous and a homozygous recessive will yield a ratio like the one we see here. So by that logic, we can conclude that Joanna is also a heterozygote, because a monohybrid cross between her parents, a heterozygote and a homozygote, will never yield a dominant homozygote. So her genotype is big A, little a. So now that we found that out, we can do a monohybrid cross between her and Tom, who is homozygous recessive, to determine the probability that their child will manifest the trait. So Joanna, the heterozygote, and Tom are crossed. The only two possibilities we can have is a completely recessive offspring or a heterozygous offspring. So the conclusion we come to is the child produced between Tom and Joanna will have a 50% chance. And that is all I have. Thank you very much.